Hi friend, how are you? Today my discussing topic is about induction motor as a transformers. What is the difference and what is the similarity in between the induction motor and transformers discussed today? An induction motor similar to a transformers in many respects. If we are considering the induction motor with both its stator and rotor winding in star, as this diagram, we are considering this is the stator of the motor and this is the rotor of the induction motor. And here E1 and E2 is the induced EMF, electromagnetic force, induced EMF, and let's discuss about what happening, how to produce this EMF inside the stator and rotor. The rotor winding assumed open circuited. This rotor winding are assumed first open circuited. Rotor current is zero. No electromagnetic torque will be developed. Because the rotor is open circuited, so no current will be flow on the rotor circuit and no electromagnetic torque will be developed. By applying the three-phase balance voltage, in the stator circuit with the frequency F1, so if we are applying the three-phase balanced AC supply to the stator winding, the electromagnetic rotating magnetic field will be developed. This rotating magnetic field will produce a flux, and this rotating flux cut both the stator and the stationary rotor conductor at synchronous speed. Okay, this stator we are applying the stator and three-phase supply, and this three-phase supplying produce the electromagnetic field. This electromagnetic field will produce the flux, and flux is cutting by the help of the rotating flux cut both the stator and stationary rotor conductors. So if this cutted by the stator and rotor conductor, the EMF will be induced. This EMF, as per the formula, the stator will produce an EMF and the rotor will also produce an EMF. So as per the per phase value, we are discussing about the per phase value. So for this per phase from the neutral point, we are getting the U1. So what is the formula of the U1? Per phase, the stator winding U1 equal to root 2 pi F1 KW1 N1 phi. So N1 is the stator series turns per phase and KW1 is the stator winding factor, F1 is the frequency here and phi is the flux here. Flux of the stator, flux cutting of the stator. Similarly, the same amount of flux will be generated in the standstill rotor. So if we are considering it, the E2 as this picture is concerned, so E2 will be root 2 pi F1 KW1 N2 phi. So N2 is the rotor series turns per phase, KW2 equal to rotor winding factor, and phi is the resultant air gap flux per pole. Here phi is the resultant flux per pole. Resultant flux means the stator flux is involving with the rotor flux also, so it is the resultant flux. So here by calculating this formula 1 and formula 2, if we are putting, we will get the voltage ratio E1 by E2 equal to N1 by N2. Why? Because root 2 pi F1 are same and KW1 KW2 are same, so we are omitting and neglecting the KW1 and KW2. So KW1 and KW2 is the stator winding factor and the rotor winding factor. So we are getting the formula U1 by E2 equal to N1 by N2, and this formula is for the induction motor and this formula is for also the transformer. So the same voltage ratio, same to the voltage ratio of the transformers. Transformers formula voltage ratio and induction motor voltage ratio are same. So today our discussing topic is about the induction motor as a transformers. So at no load we are getting the formula same. So, winding rotor induction motor at standstill is similar to the transformers at no load. Stator and rotor winding. If we are discussing about the stator and rotor winding, so stator winding and rotor winding has an resistance and leakage reactance, and the transformers primary and secondary winding also the resistance and reactance. So this is the similarity with the transformers. And if the transformers loaded show the secondary winding loaded transformer. Secondary winding will energized, and the secondary winding will be energized. MMF of the secondary current reacts to the primary of the transformers, and in order to draw the power from the AC source. Similarly, if the in the case of the induction motor, if the sap load is increasing, the rotor MMF reacts on the stator winding, and in order to extract the more power from the AC source. So this is also the similarities with the transformers and induction motor. And if the also the stator winding of the induction motor is treated as its primary, and the rotor winding as its secondary. Consequently, the transformers has primary and secondary windings. Also, the phasor diagram and equivalent circuit of the three-phase induction motors is most similar to the transformer. So this is also the similarities with the induction motor and transformers. The voltage ratio of the induction motor, we are already been discussed the voltage ratio. The voltage ratio of the induction machine includes winding factor here Kw1 and Kw2, because the stator and rotor are the distributed along the air gap periphery. But in the transformers, primary and secondary bring the concentrated winding and require no winding factors. So we are neglecting here, and we are just equivalent this E1 by E2 equal to N1 by N2. Another difference between the induction motor and transformer is that the no load current in the induction motor varies from about 30 to 50% of the full load current, whereas in the transformers no load current varies from 2% to 6% of the full load current. A mutual flux in the transformers completes its path through the low reluctance iron core, and the mutual flux in the induction motor has to cross the air gap between the stator and rotor. So transformers and induction motors has lots of similarities. So we are telling the induction motors similar to the transformers in many respects. So friend, we discussed about the electrical machines today, how the induction motor or is similar to the transformers. If you interested, please subscribe my channel and press the bell icon for more updated or different electrical engineering related video for the engineering student also. Thank you friend for watching my video. Thank you very much.